You're sitting in a Boeing 737, cruising at 37,000 feet. Outside, it's negative 60 degrees Fahrenheit, and the pressure is basically the same as the top of Mount Everest. And the only thing standing between you and all of that is a tube made of aluminum, roughly an inch thick. But here's the thing, that tube is an engineering masterpiece. Today, we're breaking down exactly how the Boeing 737 fuselage works, from skin to frame, nose to tail. The fuselage is essentially the main body of the aircraft. It's the tube-shaped structure that carries the passengers, crew, cargo, and most of the aircraft's systems. On the Boeing 737, the fuselage is approximately 100 to 138 feet long, depending on the variant, whether you're looking at a classic 737 to 800 or the newer MAX series. But it's not just a hollow cylinder. It's a precisely engineered pressure vessel, and every single part of it has a specific job. Let's start on the outside, the skin. The 737's fuselage skin is made primarily of aluminum alloy, specifically 2024 and 7075 series alloys, chosen for their incredible strength-to-weight ratio. The skin is thin, around 1.6 to 2 mm in most areas, but it's not carrying the load alone. It works as part of what engineers call a semi-monocoque structure. That means the skin shares the structural load with an internal framework underneath it. Think of it like your own skeleton and skin working together. The panels are joined together with thousands of rivets and adhesive sealants, forming lap joints and butt joints that create a pressurized, airtight seal. Now let's go inside the structure. Running around the circumference of the fuselage, you have the frames. These are the circular ribs that give the fuselage its iconic round shape. On the 737, frames are spaced roughly every 20 inches along the length of the aircraft. They resist the crushing and bending forces the fuselage experiences in flight. Running lengthwise, from nose to tail, you have the stringers. These long, thin strips of aluminum connect the frames and resist the stretching and compressive forces that come from the aircraft flexing during flight, turbulence, and landing loads. Together, frames and stringers distribute stress evenly across the entire structure. No single point takes all the punishment. Here's where it gets really interesting. The 737 fuselage is a pressurized vessel. At cruise altitude, the cabin is pressurized to the equivalent of about 6,000 to 8,000 feet, much more breathable than the thin air outside. This means the fuselage is constantly being inflated and deflated every single flight. That expansion and contraction creates pressurization cycles, and over thousands of flights, those cycles cause metal fatigue. This is exactly why aircraft go through rigorous maintenance inspections to catch any micro-cracking before it becomes a serious issue. The fuselage isn't uniform, different sections handle different jobs. The E-nose section houses the flight deck and the radome, the fiberglass cone at the very front that protects the weather radar antenna. Below the passenger cabin is the belly, the lower lobe of the fuselage, which houses the cargo hold and, on many 737s, a portion of the fuel system and avionics bays. At the rear, the aft fuselage carries enormous loads from the tail. The horizontal and vertical stabilizers attach here, and the APU, the auxiliary power unit, sits in the tail cone providing electrical and bleed air power on the ground. So next time you board a 737, take a second to appreciate what you're stepping into. It's not just a tube, it's a pressurized, load-bearing, fatigue-resistant structure that has been refined over decades of engineering. From the semi-monocoque skin to the frames, stringers, and pressure cycles, every detail is intentional. If you want to go deeper on 737 systems, engines, hydraulics, or avionics, drop it in the comments below. And if you found this breakdown useful, hit the like and subscribe button. There's a lot more aviation engineering coming your way.